So last time we discussed the background for concurrency and parallelism. I'd given you some definitions, talked about a brief history of concurrency and parallelism in Java. I'd also given you some tips on which mechanisms to choose under what circumstances. And now what we're going to do is kind of talk about why people would want to use concurrency and parallelism, both in general as well as specifically for Java. So we'll understand why the support that's provided in Java is beneficial, what types of problems does it solve. And you'll see that there's sort of three motivations for concurrency and parallelism. One is to leverage advances in hardware and software components. The second is to improve various software quality attributes, such as responsiveness or performance or software design structuring issues. And the third is to support various popular services and apps and capabilities in the way that we've come to expect them to behave given modern computing infrastructure. So let's talk about motivation one first, leveraging advances in commodity hardware and software. So, what does it mean to be commoditized? It means that you're able to get access to good quality componentry at a reasonable price, right? So they're affordable and easy to obtain. We talk a lot about commodities with things like, coffee beans or orange juice or stuff like that. Well, computing has also become commoditized over the past couple of decades. And one of the reasons why this has happened is because of something called Moore's Law. And what Moore's Law says is that the number of transistors in a dense integrated circuit doubles about every 2 years or so. It's a common misconception that Moore's Law says that the speed of a computer will double every 2 years. That used to be the case up till about a decade or so ago, and that's no longer the case. But it is the case that the number of transistors keeps doubling. And one of the consequences of the fact that things have slowed down, or not slowed down, the rate of improvement of speed has not increased every 2 years the way it used to. The number of transistors have continued to increase. One of the things that's happened there is we now use all those transistors in order to be able to do multi-core processing. So almost every processor you're likely to buy today is going to come with multiple cores, which is using all that silicon and transistors for useful purposes. And basically, multi-core processor just means that you have multiple instruction processing units, CPUs, that are able to process the instruction streams in parallel. This has become essential as the clock speeds haven't kept up. So this is the same diagram I showed you before. It kind of ends in 2010, but the curves are actually the same. Things have really not improved much more since 2007 or so. And we have maybe 2.83 gigahertz processors are about as fast as they'll go. You can get them to run faster if you're willing to put them in liquid nitrogen and so on in order to keep them cool. But I suspect we've probably seen the end of rapid increases in performance, at least with today's hardware fabric technology. In fact, it's gotten to the point now where silicon has become so plentiful and transistors have become so plentiful that it's very difficult to buy a single core processor anymore. Almost everybody sells them in multi-core packages, which is good in many ways, but it's also a bit concerning for things like real-time and embedded systems where they want very predictable and deterministic behavior. Oftentimes people these days will buy a multi-core processor and then disable the other cores and just have one of them run if you really need to have predictable behavior. Java 8 addresses this movement towards multi-core by the use of functional programming with fine-grained data parallelism in order to be able to leverage the proliferation of the cores. We're not going to talk a lot about that, but just interesting to see how technology evolves over time, software technology evolves over time to take advantage of the hardware more effectively. Something else that's been happening, this is now completely ubiquitous and pervasive, is that operating systems and virtual machines are also able to handle multiple cores. That wasn't the case in the early days. When I was finishing up my PhD, some of the operating systems that were in widespread use at that time still only could allow one thing to take place. Even if you had multiple CPUs, the operating system didn't know how to take advantage of them effectively. That has long since changed. Windows, Linux, Solaris, the Java virtual machine, all these different platforms, all these different operating environments all take good advantage of the underlying cores. Although, as you've probably been hearing about in the last few weeks with Spectre and Meltdown, there's a whole new set of headaches coming with the way in which people were designing the speculative computing mechanisms for the multi-core processors, or the processors in general, actually, not whether they're multi-core or not. And as a consequence, we have all these security holes. So now people are out there frantically trying to patch the software to work around the deficiencies in the hardware, which is going to cause an interesting set of headaches for a very long time. Something else that's now quite well multi-core and multi-thread enabled is middleware. Operating systems, as you probably know, include things like Windows and Linux and Java and VxWorks and so on. The operating systems typically provide a hardware abstraction layer that shields the applications and system services from details of the underlying hardware. Middleware are layers on top of operating systems that abstract away from differences in operating systems. So just as operating systems abstract away from differences in hardware, middleware abstracts away from differences in operating systems. So you don't have to worry anymore about whether you're running on Windows or whether you're running on Linux or whether you're running somewhere else. It'll shield you from that. Middleware does other stuff too. We'll talk about that later. So there's lots of middleware out there, things that you may have heard of like Spring, Microsoft.NET, J2EE, Apache, ACE, Corba, DDS, and so on. These are all examples of technologies that hide the operating system details from the programs. So the long and the short of it is knowledge of concurrency and parallelism is needed to program all these systems effectively. So part of the motivation here is really kind of push-driven. The hardware and operating systems and middleware support it, so we got to figure out how to use it somehow. The next motivation really has more to do with things called software quality attributes. So a quality attribute is basically some property of software that we want to enhance so that things work better, often in a so-called non-functional way. In other words, in some kind of quality attribute way, such as performance. So increasing performance is one of the key attributes of software. And the way we do this, of course, is by leveraging these additional cores in order to be able to overlap computation and communication. So things can run in parallel, and you actually get a speed up, a performance boost. Another quality attribute that's very important these days as we all become more attention deficit driven is responsiveness. So people get very frustrated if their computing systems take a while to interact with them. Back in the day, this goes back to the dawn of time, probably before most of you were born. We used to have computers like Windows 3.1, and if you did some long-running task like download a file, then the system would become very non-responsive. And you'd get this annoying hourglass-like or spinner-like icon. And that was an indication that you had to just kind of wait till things finished. People get very, very frustrated with that nowadays. We've all become sort of instant response junkies. And if we don't get instant response, we give up and are frustrated, right? And it's really strange to see that happening because it used to not be the case. You used to just be happy you were connected at all. So basically, the way that this affects the software is we want to make sure that our user interfaces are still responsive, even if other things are taking place in the background. And a very common way to do that is to put the user interface related tasks in one thread, typically called the UI thread for user interface thread, and then put the other processing tasks that may take longer to run, like downloading a file or whatnot, or doing some kind of image processing, put those in background threads. And then they can either run on different cores, or the operating system can time slice back and forth between them so quickly that you can't really detect that something is taking place at the same time. Yet another important quality attribute is simplifying program structure. And it turns out that there's a number of different ways to build programs to be responsive. And one way to do it is to use event-driven programming. But event-driven programming is somewhat tedious and error-prone to work with unless you're really familiar with the patterns of asynchrony and reactive software design. So often, no, not always, a more easier way of programming is to use so-called synchronous programming, where you have background threads that are making method calls and they're able to block for the duration of the call. Whereas in a reactive model or an asynchronous model, you don't block while things are taking place that run for a while. And so we'll talk a bit about how you can use threading and concurrency and parallelism in order to be able to make systems synchronous yet scalable and make the program structure easier to understand while not driving performance down the tubes. We'll talk more about the benefits of these things shortly, and I'll give you an overview of how this stuff actually works under the hood in Java and in Android. Then the third motivation for this is we want to be able to support the kinds of things we've become accustomed to using computers for. So computing is now, concurrency and parallelism is important in various contexts. So scalable, heterogeneous multi-core processing is essential for performance-intensive apps or performance-sensitive apps. And these include things like mobile gaming or image recognition. So you want to be able to make the system work maximally responsively and maximally scalably in those environments so you get a real-time experience or an interactive experience with the system. Speaking of which, sort of along those lines, we've been rewatching all the original Star Wars movies. And it's pretty funny if you look at, of course, the first 3 movies, which were done 40-some years ago or so, had very little special effects. They were very, very primitive. In fact, if you ever watch the classic lightsaber duel between Obi-Wan Kenobi and Darth Vader at the end of Episode 4, A New Hope, they're very tentative in how they're battling with each other, right? And of course, the reason for that was that the props that they had as lightsabers were so brittle that if they hit too hard, they'd break. So they kept, like breaking the props. But what's funny is if you watch the prequel series, it's really kind of cartoonish in many ways. The animation is really lame, and that's because we simply didn't have the computing power available back in the 2000 time frame in order to render high-scale 3D-looking animation. And so it's funny, if you compare that style with what we have now with the latest movies, even though the plots kind of suck, the animation is way better, right? So obviously what's happened is they decided to put all their money in animation and they left the story, behind somehow. But that's another issue altogether. So anyway, people are accustomed to high-performance computing. Parallel processing is crucial for that. Likewise, we have web servers that are used for e-commerce and social media. Those things need to be scalable. Web searching, search optimization, all that stuff depends heavily on concurrency and parallelism. And of course, big data analytics, right? Using processing to find patterns and trends and search for ways to convince you to buy stuff that you might want if it pops up on your screen, or to look for terrorist activity by monitoring phone calls and bank transactions and stuff like that. So that's kind of the performance aspect. These are all things we've come to know and love. Parallel computing is at the heart of all that. Responsive user interactions. Obviously, this is something that we, as I mentioned before, has become important. And then sustainable architectures over the life cycle. I don't know if you've had much experience maintaining large bodies of code, but if it's poorly architected, if it's poorly designed, it's really, really hard to architect and debug and enhance. Whereas if it's well designed, using patterns and techniques that are easily understandable, much more readily evolved and maintained over time. Okay, so those are just some of the motivations for why we're talking about all this kind of stuff.